The subject of this lightning talk is a project called Expressions of Change, and the link to Haskell is admittedly a little bit weak, but of course this is the Eindhoven Meetup, which is in Utrecht, so the links are already weak, I could get away with it. So it's a lightning talk. I'm going to be lightning fast, or a different way of saying it is I took like an over an hour talk and butchered it, so you'll have to kind of be quick, and I'll be quick too, so go to the next slide. So, what's the motivation for this project? So the idea is that software evolves. Your software is either going to change or it's going to be dead. So if your project is going to stay alive, then there's going to be maintenance. But of course text is static, and this is my best representation of a text file. So this of course is kind of dissing on the text file, but to be honest, the text file isn't very far away from this punch card, right? It's a static thing. There's no interaction with your compiler or your interpreter or the rest of your environment. You just show it this one thing. Okay, so when you say, okay, but we have a way of introducing history in our text files. We have Git, or your favorite version management control system. And then I say, okay, Git is this fire escape, it's bolted on. This is the solution you come up with if you have the requirements after the fact, right? You just solve it on the outside rather than integrate it. So modern buildings have these fire escapes on the inside. And I say modern programming environments should have their catering for change, catering for modification also on the inside. That's what the project is about. And the first step towards a solution is to make the modifications primitive. So change is a primitive. So there's more slogans here. The thing is, if the modification is part of the problem scope, I'd say we should make it part, which there should be kind of a mirroring part on the solution side of your equation as well. And my mirroring side is by reifying those modifications to programs, and then having your entire toolchain of programming have the interface of that be the reified modification. Okay, so the first challenge is to actually come up with some kind of formalism. What is modification? And then the second thing to do is just record everything in terms of that formalism, and then everything will be profit automatically, right? So there should be a gnome there, which is like a South Park reference. In any case, there are some thoughts about this profit. So first of all, there's the idea of having change-aware tools. Let me actually click this thing so I get a timer. Yeah, so the first thing is change-aware tools. The other thing I'm not going to talk about in this talk. So change-aware tools is you basically just take your regular set of tooling and then you make it change-aware, right? So for example, you have static analysis, which tells you some kind of information about something about your program without actually running your program, and that's great, and it usually also tells you where something is wrong in your program. And now my contention is, if you do this, if you reify modification, it will also tell you when something went wrong in the program. So it will point at a specific modification that created a specific problem. And both those questions of where and when are very useful in actually figuring out why it's wrong and then solving the problem. So it's just adding another axis of figuring out what's wrong. That's the profit. The other thing I'm not going to talk about, so that's that slide. So we actually need to reify modification, and to do that we need to figure out what modification to what are we talking about, right? Modification is going to try to come up with some formalism of construction, but construction of what kind of structures? Are we talking about Haskell programs? Are we talking about Java programs? Well, I'll talk a little bit about that, and then I'll show a particular design for the actual modifications, or rather for the actual vocabulary of modification. So the structure is S-expressions. I see at least one person cheering. First I'll tell you what they are. So an S-expression is just recursively defined as either an atom or a list of S-expressions. So an atom is just a piece of text, and a list of S-expressions is a list commonly denoted with parentheses. So here we have an S-expression which which is a list expression. So this is a list expression which consists of these three further S expressions, two of which are atoms and one of which is a further list expression. So why would you pick S expressions? Why not something more advanced? Well, the fact that there is a minimal definition makes it easy to kind of jump ahead to I'm kind of putting this whole problem of REIFY and modification on my shoulders, so I might as well take something extremely minimal to take as a playground. They also have an very explicitly they have an explicit structure in the sense that when they are printed, you can point at where the list expressions are just in a very stupid way by looking at the parentheses. And this is helpful when you're having your programmers actually doing structured modification on your program. They need to know what they are doing. And if the syntax definition is super complex, then this link between what they are doing and what's happening on screen becomes much more long or weak, and then it's much harder for them. And so finally, we actually have a bunch of languages which are defined in terms of S expressions, so that might come in useful when talking about programming languages. So, well, I'm just going to skip very quickly over this, but I'm going to stop saying vocabulary of program modification. I'm going to use this word CLEF. It's taken from musical notation. So, and this is, we'll just also use S expressions to show how these things get modified. So here is a bunch of modifications. This is the thing where we delete something at position 5 or something. And here we delete some, here delete at position 5. And here there's also, those things can be put in a list, so you can do a bunch of them sequentially. So, I'm not going to talk about all my design goals except for one, which is composition, because then I can show you the slide of Erik Meijer, who says composition is the essence of programming, which is an awesome quote. And I also want to show this particular slide, which is thinking a little bit about the kind of cross-section of composition of program structure, which is a well-studied idea. And now I've kind of introduced this idea of program construction, right? So these constructs of how to modify your program, they might also themselves be composable. And in fact, there might even be a cross-section between how is your program structured and how is the way you manipulate your program structured. And one thing you could think about, for example, is if you have a program which is a bunch of modules, which is a bunch of classes, which is a bunch of methods, statements, all the way down to maybe actually an atom. So you want to see the history at each of these levels. You also want to see how these histories interact. So you want to see, okay, what's the history of my method? And why is this particular action done in this particular method in the grander scheme of the module that it is in? Those kind of questions I think are useful to ask in terms of program understanding. And Erik Meijer agrees with me. So here's the definition of the CLEF. So I'm going to quickly skip through it because it's a lightning talk, right? So you can, the atoms can come into being, then they can be changed. The list expressions can also come into being, and we can insert new parts into the list expressions. And of course, a key thing here is that the thing we're inserting is expressed again in terms of history. So we're not just inserting a piece, a structural thing, but we're inserting a further thing to be played, interpreted by our kind of means of construction. We can delete that position, and we can also extend the history. So after it's been something's been inserted, we can kind of continue the history from there on. And we have a mechanism of composition in the historic level. So now I'm going to scare you by doing a quick thing, and I'm going to do it slowly. So the quick thing is just to show you, this is stuff moving through time, and then here we see, the historic view, and here we see the thing that's actually being constructed. That's going to be the example. So here we have the become list. Something comes, a list comes into being. Then we insert at position 0. We don't know what we're going to insert yet, so we kind of create a piece on the stack or a scratch pad or whatever you want to call it. A new list comes into being, and then in that list an atom is created and a new one is inserted. Actually, I'm kind of cheating here, right? There should be another piece on the stack. Another atom, and then it gets pushed back. We insert at position 0 another atom and another one, and now we can extend the history. We take the thing that's already there and put it on our stack, and we extend it and we push it back. So, why would you do this? Well, we'll come back to Erik Meyer and his composition, in the particular one. So let's think a little bit about what the two kinds of composition, the two main kinds of composition these axes in this table are. So, first on the right hand side we have the structure, and we've kind of already seen it. So, the main means of composition in S expressions is the list expression. So here is the list expression, and here are some parts. So it's the atom, well, we saw that. And here we have the main means of composition over the means of construction, and that's the thing I call the score, but it's basically just a bunch of modifications, and these modifications are here. So now this whole thing on the left translates to that thing on the right. And now the kind of question is, if we look at something on the right, like this particular little atom, can we find corresponding pieces on the left? And in fact we can. Here it's super trivial because it's just one thing, and here it's also trivial. But here we see that the history of this sub-expression is actually contained in this greater thing, and we can, when we view this thing, we can click on this thing and just hide all the things that I showed in dark gray here, but hide them completely and show that what is the history of the sub-expression. I might do a demo if you're up for it. I'm not sure what the time situation is. It's always dangerous, demos. So, the example, well, use the same kind of right-left distinction. So we can add a list here, and we can add, I don't remember the particulars of the actual atoms I used, but I remember there was 2 atoms here, and then kind of return. So by the way, now you're seeing on the right you're seeing the structure under consideration, and on the left you see the history of that particular structure is kind of always moving with whatever happens to be selected.
Yeah, I guess history is something that you can never edit.
Well, so well, not in this demo, but the idea is of course to that you can just take the thing on the left, which happens to be an S expression, move it one panel over to the right, and get another panel on the left, and go a little bit deeper into it. Which is kind of, it's not just a joke because we like recursion, right? There's a, for example, in Git, there's reasons to rewrite history, which are good reasons. But if you rewrite history in Git, then you lose a lot of the advantages of Git in terms of safety, because there is no kind of Git over Git. So I'm saying you should have, like, at some point it kind of becomes useless. But the technology shouldn't specify what that point is, just kind of how deep you want to go yourself. How many. Okay, well, I can show you more of these, but I kind of think the idea is clear.
Is there but the mapping isn't one-to-one, right? Because you can have multiple histories for any expression that you.
Yes.
So how do you? Because you type ASDF there, and then this generated some history.
Yeah.
So you just you have making atoms for atoms, and then how do you define what is the obvious history? Let's say.
Yeah. Doesn't it converge to like a minimal? Like, is this like a kind of like a term rewriting thing, right? Like in many cases, you can converge them to like a shortest path.
Sure. So there's multiple questions. So the first question is, how do you? There's just specific commands which translate basically into things on the left. You just happen to see them on the right first when you're typing, and then like everything I do is just a particular thing on the left, right? It's just a word from the vocabulary of change. From the editor, you can only do things that are.
So this is a structure editor.
Yes, by necessity, basically, because kind of the belief is that you should not allow any modification, but you should kind of constrain yourself in which a small subset of useful modifications, and then have your editor record those, right, on this profit slide. So you just. Of course, that's the first step, and then basically your question, or kind of part of your question is like, maybe a question before your question is, if you do that, then you create a whole bunch of stuff, right? If I now decide this is AXDF is nonsense, I remove it. But if I want to create a commit and share it with my coworkers, then in this history, the fact that I've actually removed it is still present, and the fact that I've added it is also still present. So then you want to offer a set of tools that offer you choices in whether you want to present that. Like often when you communicate with your coworkers, you probably don't want to show all your mistakes. But there's a level in history where you do want to keep mistakes around, right? Because, well, if it went already in production and everyone is confused, if you just kind of brush it away, then you don't want to. So there, but that should be. I think that should be kind of policy or politics, either one. So it's a different. It's not a technical question. Yeah.
So on the right-hand side, we can structure programs by putting expressions and functions and making modules and stuff. And this is actually something I miss in Git sometimes, where you probably don't want to record every individual keystroke, but can you sort of structure the history then?
Yeah, so
yeah,
not in this demo again, unfortunately, but the bottom node on this list, on this CLEF, right, so it consists of nodes which are kind of mechanisms for modification, and the final one was a thing called chord. So the idea is basically to arbitrarily group nodes into a single node, which can then further be arbitrarily grouped into whatever way you see fit. So now in Git you have a commit, which is the own. Well, you can branch and then merge, but there's a very different intention behind that. But in terms of organizing stuff in time, you can only say there's a commit, there's a commit, there's a commit. What you would want to say is these three commits, or whatever granularity you want to call it, these three things, they together form another logical unit. And that's the idea of these chords, where you can organize things hierarchically in time, so to say.
How would you merge like two histories there?
Yeah, so that's another question where I think kind of this approach has an advantage and a disadvantage. So I think the advantage is that there's super granular information available, and for example, if I were to add here, say, if I were to add, this is what I add, and then my coworker goes here, well, to confuse you, and he can type, right? And now I'll just put this on one line to drive the point home. So now in Git this is hard because it's on one line and we don't know what to do anymore. But if it's structured, then it's much easier to see that these two things are different in different places, especially because there's a separate, there's an element in between. That's the part that makes it easier. The part that makes it harder is kind of relating to your, or both of you were hinting at this idea, that there's multiple ways to create a single structure. So there's multiple paths, well there's infinite paths to create any structure. You can always add and remove arbitrary stuff, right? So the question is, if multiple paths lead to the same place, is it even the same thing, or should you, I'm not sure yet.
It would be useful to have like a button to be like, choose the minimal path.
Yes,
like,
that's a useful button, and in terms of merging, you could have like this, the merge, there's different paths, but, or you could have basic settings, right? If the paths are different, but the answer is the same, then always just merge it and prefer either one. By the way, I think one of the things that hopefully are easier in such an approach is cooperative editing, because, well, in Git you have like 1 hour commit granularity or something along those lines. But exactly because you have such super granular information available, I have some hope that there's that it's easier to make cooperative editors. Now there are some attempts at it, but I've never found one that is not just kind of breaking within the first 10 minutes of usage.
Google Docs.
So,
But for programming,
How do you feel about tools like MPS and projectional editing and model-driven software development?
that's a lot of questions. I kind of ended up, I kind of came up with the problem or the idea of modification first, and structure. I'm doing structure editing only by necessity, right? I'm not like a big believer in structural editing. It's just that if you want to if you want to reify a modification, then you kind of already you're almost forced to do structure editing. So I should probably look into other structure editing editor tools and how they solve it more deeply, or how they kind of where
I don't know if they solve it.
yeah, where they fail also,
Yeah.
but
Yeah.
yeah.
so you said that this could be helpful to have tools that are based on the change, also like static analysis, compiler. So do you have try to make some kind of beginning or of something that would...
Yeah, so I played a little bit with static analysis, like undefined variables or unused variables, kind of super trivial things, and I got some results. So the first thing is, the first observation, so to say, is that you can always take any static analysis and just do it all the time, like for any modification. This is kind of a naive approach, which has very low cost in terms of new development, at least if you take a list of static analysis. But it is also not a maximum amount of information. So I've also explored a little bit this kind of how can you express the ways the information flows incrementally from nodes up and down a tree. But I think it's kind of a very big subject. But
for this simple thing, for example, like undefined variable, you could do it incrementally, right?
yes.
And it's actually an advantage to have it.
Yes.
The history.
Performance advantage, as well as kind of like there's one of my ideas is to kind of like there's multiple analyses that you can do, and then these analyses also depend on each other. So that's where it gets hairy, but also interesting. You can also kind of show to your user like this thing broke because this other piece of information changed because of this change, etc. Hope that was useful.
Yeah, thank you.